All right. So, hey everyone, welcome to this monthly session series. We call it Axel Edge. So, what we basically do is we have one of our SMEs present to us on a topic which is currently uh, in the talks or in trending, or maybe there's a launch around it, or things in those regard, right? So, for this month's session, we have Divesh, who's going to be presenting to us about the Kafka world of things. So I'm sure everybody has heard about Kafka and the magic it is playing in the market currently. So he'll be talking more about how to kind of streamline that and how to tune it, turbocharge it, and things like that. But before we get started, let me introduce myself. My name is Siddharth Mahabal. I lead the customer experience and enablement practice here at Axel Data. And I am your go to guy for everything that is enablement and training. A quick couple of notes from my side before I hand it over to Devesh. We have a network portal where we host all of these documents that our SMEs create, our solutions engineers create, our support guys create various knowledge articles and all those things. So I would urge you to kind of go ahead and log on to our network portal, which is right about here at the top. And then you also have an academy which we run. So there are different instructor-led sessions that we run. We have a monthly series. We have specific custom sessions and the likes of it. So those kind of sessions, we would encourage you to come to us and uh, ask for it, and everything's on the house. So we'll be happy to host you on sessions like those. So with that, I have my contact information at the bottom. I'd also maybe ping you in the chat box, message box, and then you can go ahead and let me know in case of any questions, queries. So I'll not take much time. Divesh has a pretty wide agenda to cover. So for the next hour or so, give or take, we will be hearing from him about Kafka and how to fine tune it. Okay. So with that, I'll hand it over to Divesh. Divesh, the floor is yours. Take over, man. Thank you.
Thank you so much, Siddharth. Thank you for having me. Okay, so hello everyone. Welcome to our technical workshop for Apache Kafka. My name is Devesh, and I'll be your host for the next 45 minutes to 1 hour. Okay, in this particular session, we are going to deep dive into a practical performance tuning and strategies that you can immediately use to your Kafka clusters. This session is specifically designed for the platform engineer, DevOps team, data engineer who are already working with Kafka and production and wanted to take their performance to the next level. Okay. Whether you're dealing with throughput issue, latency problem, or consumer lags, we will cover those concrete solutions today. Okay. So let's get started. Okay. So before we jump in, let me set the expectation for what you will get out of the session. By the end of the time together, we'll have four key capabilities. First, you'll understand the Kafka architecture at level that help you diagnose the performance issue. We are not just memorizing config parameters, we are learning why they matter. Second, we will have the most impactful tuning strategy for production, consumer, and broker. uh, these are the settings that gives you 3x 5x or 10x improvement. Third, we will cover the advanced platform optimizations like JVM tuning, operating system configuration, which impacts, and infrastructure decision that many team overlook. And finally, you will walk with the monitoring strategy and configuration that we can implement this week. Okay, so this is immediately actionable content, and let's look at how we'll cover all this. Okay. Agenda. Okay, so here is our roadmap for the next 45 minutes. We'll start with 7 minutes of the Kafka architecture fundamental. This fundamental is critical in every optimization that we discuss, and later will make sense, but you understand how data flows through the systems. Then we'll spend the next time on the producer tuning. This is where you will see the biggest performance gain. And then we will cover the consumer tuning, focusing on fetch settings and lag management. Many teams struggles with the consumer lag, and we'll show you how exactly and how we address it. And on the broker configuration and pattern designing, getting the partition count right is one of the most important decisions that you'll make. You can't easily change it later. Okay. And on advanced platform tuning, we will see the JVM tuning, operating system storage, network optimization, and this is where we go beyond the Kafka configuration into the layer underneath. Okay. And finally, wrapping up with the monitoring essentials, we are going to show you that how we are using Pulse to monitor the Kafka, and then we will hold for the question until the end. Okay, so let's get started. So this is the Kafka architecture overview. So let me start with the fundamental questions. What is Kafka architecturally? Okay. At its core, Kafka is a distributed system with three main components. Okay, we have producer sending data in, broker storing the data on the disk, and consumer reading it out. But here's why make Kafka special. Topics are divided into partitions, and partitions are replicated across multiple brokers. You can see in the diagram we see three broker where broker 1 is the leader for the partition and the broker 2 and broker 3 are follower who are replicating the data. And this is managed by Zookeeper in older version or Kraft in Kafka 3 and beyond. Why does this matter for the performance? Three key reasons. Okay, first, more broker mean more parallelism. If you have 10 broker, you can have 10 different leader handling right simultaneously. Second, more partitions mean more consumer parallelism. Each consumer is a consumer group that can read from one or more partitions independently. Third, this is the important replication gives you durability, what it comes to at latency cost. When you write with x equals to all, you are waiting for those follower to replicate the data beyond acknowledging. Understanding these trade-offs is essential for tuning. Let's look at how data actually flow through the system. Okay. Kafka write path. Let's trace a message for your producer application all the way to being stored on the disk. This is critical for understanding where the performance bottleneck hides. So in the step one that you are seeing, right? Your application creates a message. Okay. Kafka serialize the key and value to bytes and run it through the partitioner to decide which partition it goes to, and puts it an accumulator. This is a buffer where the message batches up. Okay. In step 2, Kafka wait until either the batch reaches a certain size or timeout expiry. This is the compress. Then it compress the entire batch using the algorithm like LZ4 or Snappy and send it over the network to the broker. In step 3, the leader broker receive this batch, and here's what it gets interesting. Here is where it gets interesting. Kafka writes to the operating system page cache first that RAM append to the log segment file to the disk. If you are using ag equals to all, then the leader also wait for the follower replicas to acknowledge. In step 4, finally the broker send an acknowledgement back to the producer with ag equals to 0. That's where no wait. There's no wait. With ag equals to 1, you wait for the leader. With ag all, you wait for all in sync replica. Now look at the bottleneck table. If you are sending small batch with no wait time, you are marking too many network requests. If you're using the wrong compression algorithm, you're wasting CPU or bandwidth. If ag all with many replica, you are paying latency cost. Every optimization that we discussed today, addressing one of these bottleneck. Let's look at the read path. So now let's see how consumer read data. This is equally important for performance. Okay. In step 1, a consumer send a poll request with three key parameters. First is the fetch min byte says give me at least that much data. Fetch max wait ms says but don't make me wait more than this long. And max poll record limits how many records to return. Okay, in step 2, the broker try to read the page cache first, and if the data is still in RAM, which is usually in for recent data, this is incredibly fast. We are taking single digit millisecond if the data has been flushed to the disk and the page cache doesn't have it. You're reading from the disk, which is 10x to 100x slower. Step 3 is the Kafka send the compressed batch over the network to consumer. And the step 4 is the consumer decompress then deserialize the process, your business logic, and commit to the offset. Okay, the key inside here is zero copy optimization. In traditional system, data goes to the disk to kernel space and kernel space to uh, application space back to the kernel space, and then kernel space to the network. For 4 copies, Kafka does this in 1 copy using sending straight file from disk to page cache to network. This is why page cache is absolutely critical for reading performance. Your RAM isn't just the JVM heap. Most of it should be left for the page cache. Also notice consumer parallelism is limited by partition count. If you have 10 partition and 20 consumer, 10 of those consumers are idle. This is fundamental design constraint. Okay. uh, Partition architecture and the data flow. So let's zoom into the partition because this is the fundamental of Kafka scalability. Look at this example. We have a topic called order with the 3 partition. Okay. Uh, each partition in an order immutable sequence of message. Message 0 goes to the partition 0, message 1 to the partition 1, message 2 to the partition 2. Then it wraps around. This is the default round robin behavior. Now with a replication factor of 3, each partition have a leader and 2 follower. For partition 0 and broker 1 is the leader and all reads and writes go through the leader. Broker 2 and 3 are follower who replicate from the leader. The ISR in sync replica set include all the replicas that are fully caught up with the leader. This matters for ACK equals to all. Here, the consumer group assignment, if you have a consumer group with 3 consumer and 3 partition, you will get one-to-one mapping. Okay, ideally. But notice what happens if you have more consumer than partition. Consumer 3 is idle. That's not consuming anything. This is the golden rule. The number of active consumer is limited by number of partition. Look at the performance implication table. Too few partition, you can't scale consumer. You hit a bottleneck. Too many partition, you get memory overhead over the broker for managing all those partition objects. Sweet spot is usually 2 to 10 times of your broker count and at least as many as you peak expected consumer. This is one of the most important design decisions that you will make, and it is hard to change later. Let's look at how Kafka actually store data. Okay. Uh, let's look at what actually happening on disk. Okay, each partition is a directory containing multiple log segment file. You can see here sorry, you can see here partition 0 has these .log files, okay, which are mentioned here, and those are actually message data plus .index and .time index files that are for fast lookups. Okay, when a producer message arrives, Kafka append it to the active segment where the page cache and eventually flushes to the disk asynchronously in batches. This is why Kafka is fast in doing sequential write, not random write. Here the key insight, page cache is the king. If your data is in page cache, read are 0 to 1 millisecond. If Kafka has to go to disk, then you're looking at 10 to 100 millisecond. That's a 100x difference. Okay, the recommendation is size your RAM to hold your active data sets. If you're writing 100 GB per day and consumers are typically reading same day data, you want at least 100 GB of RAM for page cache. Okay. Also notice the disk IO pattern. Kafka does sequential write. Even hard drive can do 100 MB sequentially. But if consumers are caching up, reading old data scratches across segments, HDD drops to 1 MB per second, and this is why SSDs are critical for perform production. That key handles random reads much better. Okay, now let's talk about where things go wrong. Okay, common bottlenecks. Okay, based on hundreds of production Kafka deployment, here are the most common bottleneck that you will encounter. Network I/O. This network I/O is usually the first culprit. If you're seeing high network utilization but low throughput, you are probably sending small message without batching or compression. The fix is producer batching. Disk I/O becomes a problem with slow disk or poor file system configuration. This usually show up as latency spike when page cache misses occurs. The first fix is RAM for page cache or switching to SSD. CPU and memory issue typically manifest as GC pause. If your heap is too large and you're using wrong garbage collector, you'll see periodic freezes. The fix is right sizing your heap to 6 to 8 GB or usually G1 GC using. Design issue are the hardest to fix because they are architectural. If your partition count is less than your consumer count, you literally cannot scale horizontally. If you have hot partition where one partition gets way more traffic than others, you need better partition logic. Use this quick diagnostic guide. High network with low throughput means batching problem. High disk with latency spike means page cache issue. And frequent GC pauses means heap problem. Uneven partition load means design problem. And consumer lag growing means you need more consumer or async processing. All right, now let's understand the architecture. Now that we understand the architecture, where the problem hides is, let's start tuning. We'll begin with the producer. Okay. So let's talk about the producer performance. This is where you will see the biggest gain. We are talking about 5 to 10x improvement with the right setting. Fundamental trade-off is throughput versus latency. Do you want to send message as fast as possible or do you need them delivered with minimal delay? Most system optimize for throughput because the latency cost is acceptable. Okay, we are taking extra 5 to 10 millisecond. The key decision is how much to batch before sending, how long to wait for full batches, what acknowledgement level to use, and whenever to compress the data. Let's dive into the most impactful settings first. Batching. Okay. There is a single most important producer setting is if you change nothing else, change this. This key is batch dot size. Control how large a batch can grow. This is the default is 16 KB, which is way too small for producer. I recommended 32 to 64 KB. Why? Because larger batch means fewer network requests, which means lower overhead per message. And the second is the linger.ms. Okay, linger.ms controls how long the producer will wait for the batch to fill up. The default is 0 second, 0 cents immediately, but if you set this to 5 to 10 millisecond, the producer will wait a bit to accumulate more message into batch. This dramatically improve the compression ratio and throughput. Buffer.memory is the total buffer space for batching. Default is 32 MB. I recommend at least 64 or higher to handle traffic spikes. Look at the real world example. Before tuning with 16 KB batch, no lingering, this team was getting around 18,000 messages per second. And after changing to 32 KB batch and 10 millisecond linger time, they are hitting 1 lakh message per second. That's 5.6s improvement. Okay. The trade-off is they added 10 millisecond of latency, but the most application going from 2 millisecond to 12 millisecond latency is completely acceptable if you are getting 5 to 6x throughput. Okay, here's the thing: the setting is almost free. You are not buying more hardware. You are not adding infrastructure. You are just telling Kafka wait 10 millisecond and send bigger batch, and you get a massive improvement. Okay, so next is producer acts. Okay, now we need to decide how reliable do we need message delivered to be. This is the ACK setting and it directly trade reliability for latency. Okay, remember for our architecture design, you have a leader and follower. With Act 0, the producer design wait for any acknowledgement. If first and forget lowest latency around 1 millisecond but zero durability. If you have broker crashes before writing to disk, your data is gone. Use this only for things like metrics or non-critical logs. Act 1 means wait for the leader to acknowledge. This is the default and provider provides a good balance about 5 millisecond latency, and your data is safe as long as the leader doesn't crashes before replication happen. This is appropriate for most workload. Act all means wait for all in sync replica to acknowledge. This is the safest option if the leader crashes. The followers have the data, but it's also slowest around 15 millisecond. Because you're waiting for network round trips to multiple broker for critical data like financial transaction, you want all acts. Okay, with minimum in sync replica equals to 2, that means even during write you need at least 2 replica in sync. So you can survive one broker failure during write and 2 broker failure at rest. For most workload, ACK equals to 1 with retries 3 is perfectly fine. You get good performance with reasonable reliability. One more trick is enable idempotent. The prevent duplicate message if they retry. It's basically free. Just set enable idempotent equals to true. Okay, let's talk about the compression next. Okay. Compression is another massive win. The idea is simple. Compress data before sending it over the network. Store it compressed on the disk, and let's compare the algorithm. None means no compression, only this is your data that is already compressed, like if you are sending image or video. LZ4 is my default recommendation for almost everyone. If you use low CPU, give you 2 to 3x compression and it is very fast. This is the sweet spot. Snappy is similar to LZ4, slightly different trade-off, also a great choice for low CPU environment. Gzips gives you best compression ratio 4 to 6x, but it's CPU intensive. Use this if you are paying a lot of bandwidth or storage and CPU is cheap. ZSTD is the newer available in Kafka 2 plus 1 and give you excellent compression with reasonable CPU uses. It is becoming more popular. This configuration is simple. Compression.type equals to LZ4. On the producer side, on the broker side, set the compression equals to producer to keep whatever the compression for the producer use. Look at the real world example. Okay, uncompressed, this system was pushing 1000 MB per second. This is what 8 GB per second of the network traffic. With LZ4 it dropped to 400 MB per second to 3.2 gigabyte. This is the 60% bandwidth saving with less than 5% CPU increase. Bonus, the data is stored compressed on the disk, so you also get 60% storage saving. This is an easy one algorithm. All right, now let's switch gears and talk about the consumer. Okay, so on the consumer side, the goal is simple: keep up with the incoming message rate, or ideally go faster so you can catch up if you fall behind. The main challenge is fetching data efficiently from broker. Managing consumer lag when you can't keep up, the maximize parallelism access across your consumer group. Remember, for our architecture decision, consumers are limited by partition count. So if you have 10 partition, you can have at most 10 active consumer. Let's optimize fetching first. Okay. Consumer fetch setting. So consumer fetch setting control how data is retrieved from the broker. Get these wrong and your consumers are constantly making tiny network requests. Get them right and you're fetching large chunk of data efficiently. For key parameters, fetch dot minimum dot byte tells broker don't respond until you have at least this much data. Default is 1 byte, which is unless I recommend 50 to 100 KB. This means fewer network round trips. Fetch max wait millisecond. Work with fetch min byte. It says give me 50 KB of data or wait up to 100 millisecond, whichever comes first. Default is 500 millisecond. I recommend 100 to 200 millisecond. You don't want to wait too long if there are not much data available. Max poll record limits how many records to return in a single poll. Default is 500, But if you can process messages quickly, but bump this to 1000 to 5000. More records per poll means better throughput. Max partition fetch bytes control how much data to fetch per partition. Default is 1 MB. I recommend 2 to 5 MB. Remember, if you have 10 partition assigned to one consumer, this is per partition. So you could fetch 20 to 50 MB total per request. And here's an example configuration that typically gives you 2 to 3x consumer throughput improvement. Fetch min byte to 50 KB, max wait to 100 milliseconds, and max poll record to 2000. And max partition fetch bytes to 2 MB. This is the key insight. Reduce the network number of round by fetching larger chunk of data less frequently. Your network is fast use, it bursts rather than constant small requests. Okay. Now let's talk about the consumer lag. Consumer lag is when you consumers are falling behind. The offset they are reading is far behind the latest offset in the partition. This is one of the most common problem teams are facing, and there are three strategies to fix that. Okay. First one is scale consumer horizontally. If you have three consumer reading from six partition, each consumer is handling two partition, and add three more consumers so you can have total six. Now each consumer handle just one partition, you have doubled your parallelism. But remember the golden rule, you can't have more active consumer than partition. If you have six partitions and 10 consumers, four of those consumers are sitting idle, doing nothing. And strategy two is async processing. Separate the fetch logic from processing logic. Your consumer thread quickly fetches message in 10 milliseconds and hand them off to the thread pool. Worker threads then process the business logic in parallel, which might take 100 milliseconds. This is the decoupled consumption from processing. Okay. Strategy 3 is increase partition count. But be careful, you can't decrease partition count later. Plan ahead. If you're starting a new topic, I recommend at least 30 to 50 partitions for production system. Now monitor the lag. Watch these metrics. Record lag max tells you maximum offset, lag across all partition, and alter if this goes above 10,000 or whatever makes sense for your system. Fetch latency average tells you how long the broker is taking to respond. Should be under 100 millisecond. Commit latency average is how long the offset commits take, should be 50 millisecond. And record consumed rate tells you your consumption rate if it is trading down. Something's wrong. Set up an alert on those metrics and don't wait until user complain about the stale data. Okay. Broker and partition design. Now we are getting into the foundation of the Kafka cluster. Poor broker configuration can create cluster-wide bottleneck that no amount of producer or consumer tuning will fix. Three critical areas are there: threading, cores, and network and replication. I mean, threading, cores, and replication. Okay, so threading is num network thread should be 1 to 2 per CPU. These threads handle network IO, and num IO thread should be about 2x your CPU cores. These threads handle disk IO. So on the 16 core machine, you might set network thread to 16 and IO thread to 32. Second is the network buffer, socket.send.buffer.byte and socket receive buffer byte. Control OS level socket buffer and set these to at least 1 MB each. Replication. Minimum in sync replica equals to 2 means you need at least 2 replica in sync to accept write. With a replication factor of 3, you can survive one broker failure during writes. These settings are per broker and affect your entire cluster. Get them right once during initial setup, but the most critical design decision is partition count. Okay, let's discuss that. So this is probably the most important decision, partition design. How many partitions should your topic have? Here's my decision framework. Take the maximum of three calculation. First, target throughput divided by 10. Kafka can push about 10 MB per partition reliability. If you need 500 MB total, you need at least 50 partitions. Second, you your maximum expected consumer. If you might need to scale to 50 consumer, you need 50 partition. Remember, you can't have more active consumer than partition. Third is 2 to 3 times your broker count for good distribution. If you have 10 brokers, aim for 20 to 30 partition minimum. So each broker is handling multiple partition leader. Let's work through an example. Say you need 500 MB per second throughput, might scale to 50 consumer and have 10 broker. Option 1 is 500 divided by 10. So we have 50 partition. Of option 2 is 50 consumer equals to 50 partition. Option 3 is 3 cross 10 equals to 30 partition. The maximum is 50, so you can use 50 partition. Common pitfall is too few partition mean you can't scale consumer. You hit a wall. Too many partition creates overhead on the broker. Each partition have memory footprint for tracking state, and hot partition where one partition get way more traffic than other means your partition key logic need improvement. So best practice is start with 30 to 50 partition for producer topic and plan for growth. And remember, you can't easily decrease partition count. Later, there is no safe way to shrink partition. This is architectural, so get it right upfront. Let's talk about the replication strategy now. Okay. So replication factor determine how many copies of your data exist. This is your durability versus performance trade-off. So replication factor 2 means 2 copies total. You can tolerate one broker failure. It costs 2x storage and it is the fastest option for writes. Use this for dev or test environment. Replication factor 3 is the production standard. You can tolerate 2 broker failure total, one during write if you set minimum in sync replica equals to 2, and 2 failure at rest. It costs 3x storage and write performance is balanced. RF5 means you can tolerate 4 failure and you're paying 5 of the storage cost and writes are slowest. Use this only for absolutely mission critical data. Okay. Let's understand the performance impact. With ACK equals to all and RF3, the producer sends to leader, which is about 5 millisecond. Then the leader wait for two follower to replicate, which is another 10 millisecond. Total is around 15 millisecond, which is roughly 20% slower than RF1. Okay, my recommended configuration for production is replication dot factor to 3 and minimum in sync replica to 2. What does it give you? You can survive one broker failure during writes and you will still have two replicas in sync. And you can survive two broker failure at rest and you will still have one copy of data. Plus you get balanced performance. Okay, this is good enough for most use cases. Only go to RF5 if you're dealing with truly irreplicable data. Okay, all right. Uh, Now let's talk about some of the advanced tuning that we need to do. Okay, we have to do that. We have covered the Kafka level configuration, producer, consumer, broker, partition. Now we are going to deep dive into the platform stack. This is think of it as a 5 layer stack, and top of your application and Kafka configuration below is the JVM, and below that is operating system, below that is storage disk or file system, at the bottom it is networking. We have optimized layer 5. Now we are optimizing 4, 3, 2 and 1. Expected gain is you can get additional 20 to 30% performance boost from the platform tuning. This is one of the top of the 5 to 10x gain of the Kafka configuration. Let's start with JVM tuning. Okay. So Java virtual machine tuning is critical because Kafka is a Java application. Get this wrong and you'll see periodic GC pauses that freezes your entire broker. Here's the key insight. Kafka relies heavily on the operating system page cache. Look at the memory breakdown. On server with 16 GB of RAM, you might allocate 6 to 8 GB of the Kafka JVM heap, leaving 8 to 10 GB of OS page cache. Many teams make the mistakes of giving 14 GB heap to leaving only 2 GB of the page cache. This starve the page cache and kill the performance because Kafka can't cache log segment effectively. The gold the Goldilocks zone is 6 to 8 GB heap, not more than that. If you have 128 GB of RAM, don't give Kafka 64 GB heap. Give it 8 GB and leave the rest for page cache. Use these JVM flags. Okay, XMX 6 GB, XMS 6 GB, and XMX 6 GB to set 6 GB always 6 GB of the heap. Always set minimum maximum same to the value of avoid dynamic resizing. For garbage collection, I recommend G1GC for most use cases. It provides good latency with good throughput. Set max GC pauses millisecond to 20 to target 20 millisecond pause time, and initiate heap occurrence percent to 35, which means start a concurrent GC when heap is 35% full. Full large heap over 8 GB, or if you are running Kafka 2.8 plus, consider ZGC. Okay, ZGC is something which is supported in with JDK 17 release, with the ODP that we are having, the latest release. So we can use that as well, and this is much better than the G1GC. Okay, and we have seen a significant performance improvement with ZGC, but that is one of the new feature that we are having. Okay, Linux OS tuning. Okay, so operating system tuning is where many teams don't look, but it often's the cause of mysterious performance problem. First, file descriptor. Okay, file descriptor by default Linux limit process to 1024 open file descriptor. This is way too small for Kafka. Okay, think about it. Each partition has three log file, dot index, time index. If you have 100 partition with replication factor 3, that's 900 file. Plus every network connection producer consumes interbroker is a file descriptor. You are easily exceeds 1000. The fix is edit etcsecuritylimit.com and set both hard limit and soft limit to 1 lakh. Also set fs.filemax in sysctl about 2 millisecond. Second is the network buffer tuning. Okay, the default TCP buffer is Linux size for typical workload, not for Kafka large batch transfer. Set the sysctl parameter net.core.rmem underscore max and wmem underscore max to 128 MB each. Set TCP RMEM and TCP WMEM max to 128 MB. This allows TCP to use large buffer for high throughput connection. Also enable TCP window scaling, TCP timestamp, and TCP SAC. These are the TCP performance features that help with high bandwidth, high latency connection. Third, virtual memory setting. Set VM swappiness equals to 1 to avoid swapping. Kafka should never swap. Swapping kills performance. Okay. Set VM dirty background ratio to 5. To start background flushing with 5% of RAM is dirty. Set VM dirty ratio is 80 to force foreground flushing at 80%. After applying these settings, you will typically see 20 to 30% performance improvement, especially under high load. These are set it and forget it configuration. So do them during initial broker setup. Okay. And now let's talk about the storage. Okay. Storage is critical because Kafka is fundamentally a commit log store on the disk. Let's compare storage technology. A 7200 RPM hard drive gives you 100 to 200 IOPS and about 150 MB per second sequentially throughput. This is the bare minimum. It works, and it is not ideal. The SATA SSD gives you 30,000 to 50,000 IOPS and 500 Mbps throughput. This is a good for most production Kafka cluster. And NVMe SSD gives you 2 lakh to 1 million IOPS and gives you 3 to 7 GB per second throughput. This is the best performance, but it is more expensive for most teams. SATA SSDs are sweet spot. You get massive improvement over HDD with the cost of NVMe. File system configuration use XFS with no time and mount option. No time, no airtime means don't update the access time. timestamp every time a file is read. This is a pure overhead for Kafka. So when formatting, use make fs xfs with optional stripe until unit setting for your RAID configuration. Speaking of RAID, my recommendation for Kafka is JBOD, just a bunch of disk. Don't use RAID 5 or RAID 6. Here's why. Kafka already replicate data across with RF3 and you don't need disk level redundancy. JBOD gives you 100% usable capacity. Set log.dir to multiple mount point like disk 1, disk 2, disk 3 and Kafka spread partition across them. If a disk fail, Kafka just fail over to replicate another broker. Simple. Finally, IO scheduler. For SSD and NVMe use Noop scheduler. Okay, for HDD use deadline scheduler and these are optimized for different access partition. Expected impact is 2 to 3x throughput improvement switching from HDD to SSD. This is the hardware upgrade, but it is often worth it. Okay. So let's talk about the network configuration. Okay, so network tuning is especially important if you're running Kafka across multiple data centers or availability zone. Firstly, connection management. Okay, Kafka can have thousands of concurrent connection. Set TCP max sync backlog and SOM max connection to 4096 and NetDev max backlog to 5000. Okay, this control how many connection can be queued. Second, TCP performance feature. We already mentioned window scaling, timestamp, and SAC earlier. These are the critical for high throughput connection. Add TCP fast open equals to 3 to reduce connection establishment latency. This allows data to be sent to the initial SYN packet. Third for crossing Third for cross data center replication. Use BBR congestion control. This is a network algorithm for Google that models the bottleneck. Okay, bandwidth and round trip time. Set default Q disk equals to FQ and TCP congestion control to BBR. The difference is dramatic. Traditional congestion control algorithm like cubic cause throughput is very wide and over a high latency link. BBR maintain steady throughput. Performance impact is on the local network, these settings give you 10 to 15% performance improvement. Or cross data center, BBR can give you 2 to 3x replication speed. This is huge if you're doing a cross region replication. Now, let's talk about the Kafka basic performance. Okay. So we should keep track of a couple of metrics. These are the key metrics, which is throughput, consumer lags, and the latency. Okay. Throughput is message per MB per second. This is limited by network bandwidth, disk speed, and or partition count. Latency is end-to-end message delivery time. We typically look at P50, P95, and P99 percentile. Latency is affected by batching, acts, replication, and the pauses. Okay. Consumer lags are the offset differences between the latest and consumed. So this tells you if consumers are keeping up, it's limited by partition count and consumer processing speed. Okay. These three metrics form a trade-off triangle. You can optimize for throughput, latency, durability, but you can usually can't have all three at maximum. Uh, that's it. So let me show you how Excel data is using those metrics, like how Excel data is showing those metrics. Okay. So we use Excel data pulse to monitor the Kafka. So let me share it again. Okay. So if you see, so this is the Excel data pulse where we have integrated our cluster, our Kafka cluster to it. Okay, and we can monitor. so much details and using the Excel data pulse. So if you go to the initial dashboard, you can basically identify the number of brokers, the number of controllers that are running, and the number of partitions that are available, if there are any offline partitions or under replicated partitions. Along with that, you can review the events timeline, what is latest happening on this cluster, and you can also review those metrics to identify where the most number of requests are going, read or write requests. Okay, and for each of the topic which is available, you can review that where is the most number of growth is happening, like if we have to take further decision of increasing the partition, so we can review these kind of growths. So, or if there are any issue with ISR shrinking or expanding, you can basically review that on which specific node, and then further we can review the logs that why they are shrinking or expanding. Okay, and these are the time graph, that topic by size, that most number of size that we are having is by the topic we can be reviewed, and like this we can review if there are any skewed topic as well. Okay, and the others are topic based description. Okay, in the other tab we can review that there are, if I wanted to get a detailed explanation of one of the specific topic, rather than going and running the commands in Kafka, we can review this UI. Okay, and it will tell us most of the details which are available. Okay, so we can see there are, so for an example, we can see customer underscore address table is having 5 partition with one replication factor, and all of the replicas are in sync, and the total size of the partition. Okay, so if you wanted to get more details of it, we can click on that particular topic, and it will tell us that when most number of data in and data out details, message in and message out details, replica fetch lag, as those metrics that we were discussing during the uh, earlier, right? So these all metrics are the most important. You can also go to the topic partition, broker distribution, and many more details. And if you go to the broker detail, if you go to the broker, you can basically review the health of one specific broker as well. So how many partitions are they having, how the disks are distributed, and you can also create multiple Kafka cluster into the same pulse. Okay. And let's say for an example, you wanted to set an incident or an alarm. Okay. What you can do is, let's say if the number of partition, if the bytes in and bytes out are going to a certain limit, let's say 500 MB, then you can basically create an incident out of it, and you'll get alerted when you get that. Okay. Similarly, we can also review the consumers. Okay, so for an example, consumer groups we are having, let's say the stock group that I'm having, which is having 10 members. Okay, 10 number of clients which are consuming. So let's say if we wanted to increase or decrease the number of consumer, we can review the performances are here. Okay, if there are lag which is increasing, number of consumers are there, how many clients, and from which specific topic, and what specific events which has been taken place at that time. So we can review it all just by using the Excel data pulse. Okay, so that's just a glimpse of it. So let me reshare. Okay. So uh, I'm open for if there is any other questions, and, and if there's none, I think so. Thank you so much. That is pretty much it.
Thanks for the very insightful session, Devesh. So we'll just give it a minute and see if there are any questions, and then I think we'll wrap it up.
Sure.